ครู่นะครับครับสวัสดีครับ Good afternoon everyone. I am Jompot. Today this is my second time practice for my seminar for University of Bonn, Germany. The topics that I'm going to present today is the fast radio burst. Okay, let's go. Okay, the first thing that I want to mention about is I'll be talking about this paper, like mainly. Well, this paper's name, a repeating fast radio burst, published in Nature letter in last year. What I will try to do in next half an hour is I will try to give you a knowledge what is a fast radio burst and why it's very important that is repeat. So let's go. The first thing that I want to tell you about the radio processes, radio emission processes is we have two like radiation processes in radio. First is non-thermal radiation, aka synchrotron radiation, which is you can see that this is the plot between intensity and frequency, and you can obviously you can see that the is brighter in for the non-thermal radiation is brighter in lower frequency. Another radiation process is thermal radiation, aka so-called black body radiation. That you can see that is also this one is brighter in higher frequency. So basically, if we can see the trend of radiation, like if we got a plot between an intensity and frequency, and then we just see if this one decrease with the frequency or increase with frequency, now we can know the dominated radiation here. What's the fast radio burst? The first fast radio burst was discovered by Dr. Duncan Rolimer 10 years ago, which really high intensity. Why we know that we have the parameter called SP, which is the flux density, around 30 Jansky. Jansky is just a unit that radio astronomer want to use. It's basically 10 to power minus 76 watt per meter square per hertz. Another parameter width is around millisecond, so it's very fast, like millisecond. And another parameter is dm, around 400 parsec per centimeter cube. What's this mean? This the dm is basically the basic definition of dm is written here, which is just say that Ne is the electron density and Dl is along the line of sight. So you got a source here and you got the earth here. Then this source emit the radio wave. This radio wave will propagate through the space and then it will hit the observer in the earth. Like how far is this? Is the DL here? Another, but however, we don't know the electron density distribution along the space yet. So what we want to do, so if we want to find the dm, we need to find another way. So we look into the effect of dm. Dm occur because you have an electron cloud between the source and the earth. So when you got a radio signal propagate through the space-time, and then is past this cloud of electron, this radio signal will be delayed by the factor of frequency square. So it means that the higher frequency will arrive the Earth before the lower frequency. So because now as the plot here is the plot between the frequency and time, so you can see that this a bit brighter things here is the burst. You can see that is like the higher frequency arrived the Earth before the lower frequency. Then we can find the delay time here. We know the frequency here. Now we can find the dm. Okay, fine. This is the normal plot of the fast radio burst. You can see that it's just normal plot, nothing, but it's very have meaningful one. Why it's meaningful? Because like here we got a peak, and then the peak never come again. We call it a transient phenomenon. And you can see that the width of this peak is around a millisecond. So if we want to find the energy per burst or per peak, we have to integrate the intensity during the time, like by the time domain. So basically we define another parameter called fluent. This fluent is just the area under the plot between the intensity and times. And now we can find the estimate. We can estimate the energy. How? First, I will introduce this parameter called the dm galaxy, which is this black plot here. This is the plot between dm and galactic longitude. What galactic longitude means is like, imagine that my arm is the Milky Way galaxy. If you're watching through to the Milky Way galaxy along this line, it means that you're looking to the galactic longitude 0. If you go northern, if you go to the north, the galactic longitude is increased. If you go to the south, the galactic longitude decrease. That is. So it's obviously you can see that if you're looking to the Milky Way itself, you will see more electrons basically. And another parameter is estimated redshifts that we will calculate using this formula, this equation. And in this equation, we got another one with another parameter called dmEx, the dm axis. As this name, the dm axis is the differential, the difference between the observed FRB dm minus the dm in the same line of sight. And it means that we want to get rid of the Milky Way galaxy contribution for the dm. We want to find how far this one that is, and then we know the redshift. All astronomers know how to find the distance by heart by using the basically the Hubble equation. But I want to go a bit further in detail, so I will use the cosmological model to calculate this one. And then now we can estimate the energy using this formula. This is the bandwidth. So it's the intrinsic properties from the telescope. The fluent you know already, and this one is like an area of the energy distribution. So if this one is a burst, that's just like spherical symmetry distributed in the space. So the area is the area of the sphere itself, and by the radius of the distance between the Earth and the source, which is now we call that the luminosity distance. All right, fine, so far. So what are the FRBs? The definition of the FRBs is okay. We got an observation peak in order of millisecond, so we call it fast. Makes sense. Fine. Is still only detected in radio wavelength, so we call that radio. And this energetic event, so we call it a burst. How energetic of this event is 10 to power of 30, like 10 to power of 30 joules. So to just to give you an information, 10 to power of 30 joules is equal to just in Planck scale of the Big Bang, like around like not more than 1 second after Big Bang. So it's very energetic one, and it have a high dm than the galactic dm. So what's that mean? It means that it's come from outside of our galaxy. So we call that an extragalactic source. But however, so far we detect the FRB only 18 FRBs, but still it's going on and going on. So this why we detect not many FRBs, because to detect an FRB is like a lottery campaign. You got a telescope here, you got a source here. Then this source just bursts, and then your telescope should turn there and get the information just in time. So that's why we call that. So that's why we call that the fast radio burst. It's come and never come again. It's happened, it occurred, and never come back again. And it quite makes sense, right? Because like if you got an event that as high as Big Bang, energetic as Big Bang, it's not likely to occur every day or at the same place. It's like a supernova that is just bang, and it's you cannot have a repeating supernova, right? And then so far, what we know about the FRB, like the event rate for the FRBs is they predict, the theorists detect that we will get we will get 2,000 to 10,000 of FRBs per sky per day, but we could detect not all of them due to the observation time, blah blah blah. Only one of them has been proposed with an optical counterpart by using the Subaru telescope. This one was also in nature. Why it's very important? You might notice that before that we using that formula to estimate the galactic, to estimate the DM, the redshift from DM exists, right? And then we want to check if this formula is right or wrong. So what we do is if we can find the source of 5 radio bursts, then we measure the DM. Oh, sorry, we measure the redshift of that galaxy, which is very easy, like relatively easy compared to another method. Here we can get the redshift. Then we compare between the redshift from the we compare between the redshift from this observation with the estimated redshift. That is, and we also try to estimate that. We also try to observe that using another frequency, auto frequency. Like we try to use Hertz, which is a high energy gamma ray telescope to observe that, but so far we couldn't detect anything. One of them is claimed that they detect the counterpart in the soft gamma ray by Swift telescope, but the signal to noise just fall, so we're not so sure about that. And there are no counterpart in neutrino observation. And so far we try to use like fancy telescope, but we couldn't detect anything at all. And so far, because the FRB is like a series of this decade, So what they do is they try to a lot of theorists try to predict what is the FRB. We got a lot of model of the FRBs more than the detection of the FRB itself. Like I think yesterday I just saw another paper say that yeah, FRB might come from an alien, like an alien civilization, blah blah blah. But uh, one of them, like you can find an exotic model, like there is a quantum gravity thing now, or emerging. You got some kind of like random axion star that try to commit suicide with the neutron star, blah blah blah. And this paper that repeating fast radio bursts propose that it might be a giant pulsar. Okay, but however, and why we need to study the FRBs? Like we don't mind, you just got some birds in the sky and nothing. But no, we have a lot of the application using the FRBs. Like first you can do the gravitational waves estimation, the speed of the gravitational wave, whether it's like equal to the equal to the speed of light or not. We can take the Einstein equivalent principle. We can do the magnetic field turbulence. Like we can study a lot about the cosmic web. We can find the magnetic field. We can mapping. Another one that I quite interesting is if there is a Marshall massive compact Hubble object. This Marshall will cause the FRB to have a double peak due to the lensing effect. And we found a double FRBs, a double peak FRB here. So it's quite interesting for me. The one of the application. Actually, I obtained this from the papers of the article about the Lyman alpha forest, but they use the same method. There is an FRB here, bang to the earth. You will get 1 dm, right? And if you get an FRB here, like before the cloud electron, you can find another, like you can mapping the shape of this FRB, the cosmic web. So basically, if you because FRBs is occur like a lot, so basically it means that if we got enough FRBs, we can mapping the cosmic web. Okay, what they done there in this paper is first these FRBs were detected in at using the Arecibo telescope in 2014. Then after that, the questions about the FRBs, one of the most important questions about the FRBs is because the energy is too high. So if that is true, it couldn't be repeating because the energy is this high, the source might not survive, like a supernova. Like after the supernova, the source became the neutron star. But if we can find that it's reheating, it might mean that they might use some another effect of radiation that we didn't talk about, that we didn't think about before. So we use the same telescope, the Arecibo telescope. If you are old enough, you might notice that this one is the same telescope that using for the James Bond's golden eye, but later. And what they done is, okay, first they detect that here, first here, and then they try to do the follow-up observation, but they couldn't find anything. And then they think that maybe it's like moving or something. I'm not sure what they think at that time. So they change the observed position, and they take the burst number 2 to 5 here, and they take the burst number 6 to 11 here. It looks like it's moving, or we have another explanation, because in radio it's very special observation, because you not only detect we got the how to say the field of view defined by the main lobe. So like the field of view that you see here is defined by the main lobe. So if you do something like this to your eyes, it means that you decrease your main lobe. But also, you can detect the side lobe. This is the side lobe. If there is an FRB here, and if that is bright enough, we can detect that inside lobe. So that was the same thing that happened there. Is this one might be just be very bright FRBs, and we detect that in side lobe. And then they try to calculate, because we know how to calculate how far the side lobe or the main lobe already. So we calculate, and then we see that the distance between this one and this one is around the distance between the main lobe and the side lobe of the FRBs. Fine. This is the plot between frequency and phase. Okay, look complicated. Let me zoom in. This is the zoom in one. Then you can see that in like this six and this fifth 5 bus was just in 10 minutes, and you can see that this one is brighter in lower frequency and this one is brighter in higher frequency. So we're not so sure about the radiation process of this FRB yet. So it's come to the conclusion that even we not get so many things about detecting repeating fast radio bursts, but what we know is because the energy in the burst case is too high. So it means that if that is a beaming effect, this factor is decreased. So now it might be allowed to occur in the nature. So it is a beaming like example, the good at good exam as at good example of beaming effect is a giant powerful pulsar that we studied a lot before, and it might be a galactic pulsar that give a very luminance burst. But however, the origin of the FRB is still discutable. So let me go a bit into the detail about the beaming effect. You got a spherical, like if that is a spherical one, the area is 4 pi r squared. But this if that is beaming, we decrease the area, so now the energy decrease. Makes sense. Even you got the same fluence bandwidth, but you change the factor in the last term. Makes sense then. But more and more still come. We got another report last month that they detect a multi-wave and FRBs using a multi-wavelength observation. What they done there? They're using various kind of telescope. In radio, they use not only a radio anymore. They also use the Greenback telescope in the States, and they also use our telescope, the F.S. telescope in Bonn, and they also use the VLA, the Very Large Array telescope, not only in radio but also microwave, optical, and also X-ray. This is the plot. The upper one is the plot show the detection of the FRBs. The solid circle show that it is like the FRB, and you can see that not all of them is detected. Only a few of them, and all of them was detected in radio. No detection in using the gamma ray or the optical. And still, this new burst still sometimes is brighter in higher frequency, sometimes it's brighter in low frequency. This is also the plot between the order frequency and time. You can see that it's still variable. And this is the chart that they also try to find they want to try the localization, the host galaxy of the 5 radio burst. So what they do is like if they can find any variable source here, in this solid circle, it might be a candidate of the FRBs. But so far, they couldn't find any variable source here in this black circle. The figure A represents the observation using VLA telescope. The figure B is the observation using Chandra telescope, C using microwave telescope, and D using has alpha optical telescope. So even if we couldn't detect that in another wavelength, actually it means that there is no detection. So this detection mean that if you can detect the same signal from two telescopes that separated in like 2,000 kilometers, it means that it's not something from the earth anymore. It's something far away from the sky. So it's not radio interference anymore. And so I will come to the future of FRB study after why this brought this paper. So now we know where it is. It's not like before. So because like before we have to follow up. Like you have to you want to do as before, you need to put all the telescope pointing to the same direction in the sky and hope that you detected the FRBs. But now you see a repeating one. So you just point your telescope there and wait long enough until you see some variable in the same time as if the FRBs. So now it's easier to do the multi-wavelength follow-ups also using not only in using the EM wave, you need then gravitational waves and also the neutrino follow-ups. So now it's bring all kind of physics together, and in with the next generation telescope like SKA, FAST, and Meerkat, is to bring more and more FRBs because they increase those sensitivities and stuff and so on. So it's like a lifetime challenge for me, and this is very active field of study. How active is this field? This is an paper came last Thursday, and you can see that now. Good news, we can localize if a whole galaxies of a repeating fast radio burst. And if we can detect host galaxy, we can measure the redshift and we can compare between the redshift between like estimated redshift and the true redshift. And it's come to the end of my presentation. So as a conclusion, we found a high energetic burst that can repeating in radio wavelength. But we can find one of them. That is why this paper is very important. So because like just easy name but meaningful insight. So thank you for your attention. If you have any question, feel free to ask me. Thank you.